yeah.
No, I was
Sorry.
just gonna ask you about it. Over. Thank you.
Yeah, they're doing something in my office and they have it all.
Oh, yeah, I know. I hate doing more classes all over.
So, okay. Okay, today I'm going to do a model which illustrates a couple of things, including arguments on edges and parameters on events, or vice versa. I keep confusing those. And what is a little more important is the use of state arrays as both parameters and state variables. So it's a little bit different. Typically with arrays as state variables, there's going to be a state transition, but only for one of the indices. That's typical. It's not a law of nature or anything, but that's typically what happens. And that's what's going to happen with this transfer line model that we're going to look at here. And then after that, I'm going to talk about sim event listening, which is about how instead of building a whole one event graph to rule them all, you build a bunch of smaller ones and then connect them together. And how they connected together, the idea of this is that there be a loose coupling rather than a tight coupling. And I'll get into that a little bit more about what that's about. And then our first example of that is going to be what I call the simple server component, which is basically our multiple server queue, except it's components broken up into two different components, kind of motivated by some things that we've maybe observed about our systems. So transfer line, and again in the reading this is kind of mentioned here, but it's a generalization of the tandem queue. So we looked at our multiple server queue, then we said, okay, what if we had two of them? That's the tandem queue, like a tandem bike. There are two of them, which naturally leads to the question, why stop at two? Why not more? Again, this is something which is in production sometimes described as an unpaced line. You're all familiar with the assembly line, like for automobiles and Henry Ford and that whole business there. What's different about this is that it has the same kind of structure, where the main use case for this is a situation where you're fabricating some type of item, and it has to go through a series of processes that eventually wind up with the finished item. And the difference is that each of the stations is like a multiple server queue, whereas an automobile assembly line it's sort of paced. In fact, that's one of the kind of issues with that, is that every station has a fixed amount of time, typically about a minute, to get their task done. And then, of course, what they wind up doing is, in order to increase efficiency, they will add more tasks at each station, which means that some of them don't get done until they, so it's like, if you don't get it done, then the thing just kind of moves on and it's not there. It's sort of, in a previous life, when I was kind of working more on production-like things, there was a story. You have to be careful about the incentives you have. So the incentive was, how many of these automobiles do you push out at the other end? And that was the incentive for the guy who was running that section of the line. And then this is where kind of inventory comes in. I think they ran out of carburetors, but he got his bonus based on how many cars came out the other end, whether they were finished or not. So they kept pushing cars out. They didn't have a carburetor, so instead of being able to kind of just start them up and drive them off, they had to kind of push them off to somewhere else and find carburetors for them. So just be careful. But this is, the tandem queue is one, or the transfer line is one in which it's not paced like that. So each part or customer will go to one station, kind of wait in a queue until they get served, and then they move on to the next. And then when they're finished that, they move on to the next one of those. In other words, you have one model which could capture however many of these stations that you had. Whereas our tandem queue, our multiple server queue model can only handle one. The tandem queue can only handle two. The transfer line can handle however many you want, under the same kinds of assumptions. So parameters, again, we're typical assumption as we've been doing so far. Are you going to give me the right color? No, you're not. I don't know why. Okay, so we have the arrival. The jobs are going to kind of show up in the same way as we had before. But now, one of our parameters is the number of workstations. And then for each workstation, we could have a number of different machines, and that now we're using the machine terminology rather than the server terminology, but they're interchangeable. And each station has its own service time. And again, we're going to use modern computer language indexing, which is 0 through n-1 for the machines and the service times. Now, just for simplicity, we're just all we need, the minimum number of state variables we need is this. But again, as with the tandem queue, we need to distinguish what the situation is at each station. So QI is going to be the number in the queue at station I. And so for any given situation, we're going to have, if we were to stop the simulation and kind of look at things and say, what is the state of our system? Then there would be, let's say if we had 4 stations, there might be 2 in the queue at the first station, or the 0 station, 1 at the one with index 1, 0 with index 2, and then 5 at index 3, say. So just having one variable for the number in the queue would not be sufficient, because we need to know how many are at each station. And likewise for the number of available servers, or servers, machines, again, we're going to use those interchangeably. So that's the situation with our model. And again, I want to do this. Now, when we have array state variables, that's where we use this. We will typically use this event graph equivalent of a for loop. So our run event is actually, in this case, because all of our state variables are arrays, all it's going to basically do at first is worry about scheduling our initialization. So we're going to use the same terminology as our for loop, and so our init is going to initialize, or its state transition is the initial value of each state variable. And so, again, it has an argument I, and that's going to be the index of the station that we're initializing. That is, when I say initializing, that's not a special term. In this context, initializing simply means setting each state variable to its initial value. The thing with arrays is that if we were doing this in a program, we would write some kind of for loop. But again, event graphs don't have for loops, but they have something like this. And it turns out that this is a more effective way of doing that, because of the what you need to think of is that every time there's a state transition, there's some kind of notification. We'll we'll kind of talk about that, especially in the next in the next computer assignment. We've already seen a little bit of this, like in the arrival process. Whenever you had an arrival, you would increment the number of arrivals, but then that fire property change thing, which is analogous to the action event where you click a button. That's analogous to, but not where we're doing it programmatically. Okay, so again, now, by somewhat motivated by our multiple server queue, we can, again, pick a state variable, like say q sub I, the ith element of our state variable q, and what would cause it to change? Well, a part shows up to station I, and again, notice that this is, the I here is which station is being arrived at. And the state transition is that. So now here's the thing that event graphs you need to kind of be aware of. What is it that an event has access to? What is it that an event knows about? Well, parameters and state variables, basically. That's almost it. Just by analogy to a class, what is it that a method has access to? It has access to instance variables. And as we've seen, parameters and state variables in SimKit are modeled as instance variables. And so every method, and events are methods, so methods have access to instance variables, parameters and state variables are instance variables. And that's same deal holds with event graphs. So every event can access parameters and state variables. So this arrival event has access to the Q array. It has access to the S array. But it has access to the entire array. And what we have here is we have a situation where only one of the indices is changing values. And so the event needs to know which index. Is that clear? And the index is not a state variable. The index is just whatever index it is. So we tell the event which index to use by passing it as an argument. Without this, this would be wrong. Not because this event has access to the Q array, it does, but it doesn't know what index it is. In other words, this is performing a state transition that it has actually no business doing. And if this were, if you tried to implement this in Java, you would get the red squiggly. Why? Because the method would not know what this I was. Whereas if you pass that I as an argument, then the red squiggly would go away. Okay, so the important thing I want you to get here is what is it that an event has access to? It has access to parameters, state variables, but in the case of an array state variable, and when you're only changing one of the indices in the array, you need to tell it which index it is. And that index is not a state variable. The state variable is the entire array. So you need to tell it that. Now the problem, the advantage of event graphs is that you don't need a computer or any programming language to write this down. The disadvantage is that you don't have the compiler to give you warnings when there is an error. Okay, so again, if you left out this I and tried to do this state transition, it would be wrong. It would be an error.
So if there are like 4 machines in a facility, you would just use Q1, Q2, 3, 4 in one arrival state?
Yeah, hold on, and ask that again when I'm finished with the model. Okay. Yeah, I mean, all right, so. Okay, again, motivated by our multiple server queue, the other thing that could cause queue, the ith elements of queue to change would be when it starts service at that particular station. And likewise for the number of available servers, what would cause the number of available servers at the ith station to change would be either losing one when it starts and gaining one when it ends. Okay, so can you ask your question again?
Yeah, so the event graph, like the states are the circles, right?
No.
Or
The circles are the events.
yeah, sorry, the event.
Yeah,
So if
yeah.
there's 4 machines or whatnot,
Yeah.
then you wouldn't make 4 arrival circles. You would just change. You would just under the list where it says QI, you would put Q1, 2, 3, 4. To list the.
No. See, I would. Okay, hold on to that again, and if it doesn't get answered by the time I finish the model. Yeah, see, the whole point of this is not to do that. If I have to put Q1 to Q2 to 3, then I'm gonna hard code into the model
Okay, so
what that is.
we're gonna make 4 of these that is gonna combine them one.
This is all we're gonna have.
Never mind. Okay.
This is all we're gonna have. And that's kind of the point. In other words, when we do it this way by parameterizing the stations, then we don't have to. The whole point is not to do Q, 1 for 0, 1, 2, 3, etc. But one that does it all. It's the same reason why you have arrays. In other words, instead of arrays, if I had like x0, x1, x2, x3, those are all scalars. But it's like if I start doing that, and I look and say, well, an array would be a better way to do this because I could, just as with this model, when we're finished, will handle all number of workstations. And the thing is that this, by having this argument in arrival, that means that arrival event is going to perform the correct state transition on whatever station there is, however many we have, as long as everything is done correctly. Okay, so this is all the state transitions we need. But then now to initialize an array state variable, we will typically do our for loop like thing. Remember, n was the number of stations, and notice that this is that for loop that we talked about yesterday, and this is one of the main use cases for this. So I'm initializing an array state variable, and I want to set its initial values one at a time. Okay, so then now, what about the arrivals? Well, there are, let's see. To model the arrivals, I'm gonna add, this is a situation where I need to add another event to capture the arrivals. Okay, so, and this is basically, we see this particular pattern again and again, which is why we're gonna break it apart into a separate component at one point. So, so the thing is, we need to be careful about this particular one, because this is modeling the arrival of a customer to workstation, to that ith workstation. And if we start putting a loop on that, a self-scheduling edge, then we could be in a little bit of trouble. So instead, okay, now where do we start? We come in and we start at the 0th station. Okay, so the external arrivals are going to simply schedule the first one, which is the 0th index. Now, by analogy to our multiple server queue, we know that when a customer shows up at station I, then if there's an available server at station I, then we can schedule a start service at station I. So you notice that it's the same terminology as in the multiple server queue, but with the modifier at station I added. Okay, so now this scheduling edge is incorrect so far, or not, I mean, it's not that it's completely wrong, but it is syntactically incorrect. Do you see why? So what event is it scheduling? It's scheduling the start service event. The start service event has an argument. What argument is this scheduling edge giving it? Nothing. This is like invoking a method that requires an argument, but you're invoking it with no arguments. So how do we fix that? What should? Yeah. Okay, so and what does that mean? Now, in words, that means that an arrival at station I may schedule a start service at station I, and you need to tell it what station I is. So again, the syntax here is like invoking a method. If it has 0 arguments, you can't give it any. If it has an argument, you need to give it 1. If it has 2 arguments, then you need to give it 2. And those 2 need to match. In this case, I is going to be an integer for the index of this, and so it's going to match because I started off with 0. It gave me this one, and so the 0th one will schedule the 0th one. But if I had an arrival with 1, it would schedule a start service with 1. And logically, in other words, an arrival at workstation, let's say workstation 3, is going to schedule a start service at workstation 3, not at any other one.
Is this model assuming that all the inputs follow the same path? Does that make sense? They all go to the same stations in order, or?
Yes, yeah. The model is, the way it works is like if I have, let's say here I have 3.
Okay, I just multiple.
Like that. So here n is equal to 3, and the indices are 0, 1, 2. And if n were 4, then I'd have another one, etc. So So it just goes first one, second one, you know, et cetera. Okay, the same thing here. It's like, okay, first of all, just as before, the start service event I need to tell you which index it is. And that is going to pick off the correct state transitions. And it's also going to pick the right service time, because each station has its own service time. And then, again, when I finish service at station I, I'm going to schedule another start service only at that station I if there's somebody in the queue at that station I. Okay, so now the question is, are we done? Well, what would, let's take a look at this and see how, see if we can kind of at least mentally see how this was going to behave. So we're going to start with the run. We're going to schedule a whole bunch of inits times 0. And then presumably our first arrival is going to be after a certain amount of time. So our first arrival shows up, it's going to schedule arrival at 0. So now Q0 is going to be one more. Presumably S0 is bigger than 0, so that our first guy, this is going to be true. That's going to schedule a start service passing 0. That's going to occur next. Q0 is going to now go to 0. S0 is going to be one less. And it's going to schedule an end service sometime later. Meanwhile, the arrivals might be popping in. But just focusing on this, when the end service occurs, if more guys have shown up in the queue, that will get scheduled. But something is missing. So if I have more than one station, when I end service at station 0, the first one, what should happen in addition to what's here? So here's station 0. I have somebody who's just finished. What do? They don't leave the system. They go to the next one, just like with the Cameron queue. So basically, instead of just kind of leaving, I want to schedule this next guy. But now, arrival requires an argument. What argument should I give it? Okay, so if I give it I, what will that do? That says let's just look at the very first one. If I is 0, and I have an end service event at station 0, this is going to schedule an arrival at station 0. So yeah, we're just going to keep cycling through station 0. So we need to go to the next one. We need to go to I plus 1. Because that's the next station. Okay. Now, let's look at this case here where we have n is equal to 3 and the last station is 2. So when we have an end service at station 2, and that's the last one, then what will happen if we schedule an arrival at station 3? When there is no station 3.
It's gonna crash in implementation.
Yeah, the implementation would crash. I mean, the event graphs don't crash, but the implementation would crash. So how do we stop ourselves from scheduling an arrival event where we would have an index out of bounds exception?
Less than 3 minus 1.
Yeah, so that's where the Boolean condition comes. In other words, if I is less than n minus 1, then we will schedule it, but if I is equal to n minus 1, that's the last one, then we don't do that. Okay, so now we see that the n service 0, 1 will go to 2 if there is, the n service 0 will go to 1 if there is 1. And then the 1 will go to a 2 if there is 1. And then if 2 is the last one, then it doesn't get scheduled. Okay, and that's the model. And hopefully I've done it right in the slide. Okay, so you can consult the slide to kind of see the full thing. But I wanted to do it that way to emphasize how each of these are something that you know, when you do it, it's going to be kind of similar. So I think it's important not to see, just to see the final thing, because if I just seeing the final thing say, okay, yeah, sure, that makes sense. But I hope what you got out of my doing it on the board is that it doesn't just kind of come full blown like that. Like when I make you do them, you're going to encounter a situation where, okay, you know, what do I put here, and how do I know that this is correct? Again, the things you need to be checking are things like, when I schedule an event, is there consistency between the scheduling edge and the event in terms of arguments? So if I schedule, like in this case, this arrival event had no arguments, and so I didn't schedule it with one. Whereas this arrival had an argument, and so I schedule it. Every time I schedule it passing an argument. And that argument is also, event graphs are kind of loosely typed in that way, but Java is strongly typed. And so in the implementation, obviously this is going to be an integer, and the Q's and S's are going to be integer arrays. Okay, so now here's the thing: is that even now this is still a fairly simple event graph, but what happens is, as you start to model more and more complicated scenarios, you find that you need more and more state variables, you need more and more events, and eventually you get this sort of plate of spaghetti that is less than useful. So in other words, by itself, sort of monolithic event graphs have a limit to how much you can scale them. So what is a way to scale things up a little bit more, and that is to kind of componentize things. In other words, instead of having one big monolithic event graph, to have a series of smaller components, each of which is relatively small. And when it's relatively small like that, it's easier to implement, it's easier to debug, and it's easier to really verify that in fact is what's going on. Now the thing is that when you have a situation like that, you want to have a loose coupling of the components rather than a tight coupling. What's the difference? When you invoke a method, that's tight coupling. In other words, if I invoke a method I need a reference to the object, and I need the name of the method. What this sim event listener idea is that the means of communication between components is going to be with these events or sim events. And it's analogous to what we did last quarter with action listeners and buttons. If you remember, when you click on a button, it fired this action listener, and the button didn't really know or care who was listening. And the action listener would typically also kind of only be vaguely aware of who was sending it an action event. And so that's an example of loose coupling, and it's just analogous here. So we have these events, these sim events, which we're representing in event graphs by circles. And so the idea is that every time one of those events get processed by the event list, it gets dispatched to any sim event listener who happens to be listening in. And so the kind of the default way of this is that if the listener has the same event, then it just processes it normally as if it had scheduled it. So here's just sort of a somewhat abstract example. Let's see, do I have? No, it's okay. So here's one. Here's the source event, and here's the listener. The connector, if you notice, is this kind of thing here with a little triangle at the end. There are kind of two ways to think of this. One is you can think of this as the arrow, the direction that the events are going in. The other way to think of it is to think of this little thing as a stethoscope, and you're kind of listening in on something. Either way. Okay, so this component has events A, B, and C. The listener component has events B, D, G, and F. And it's listening to this first component. Now, the way that it works is that only events that are scheduled will be dispatched, not events that are heard. So when at some point event A is going to somehow occur. But because it's not scheduled by this component, it does not get dispatched. But it will schedule events B and C. See, I think, is this the, do I have, yeah, okay. So let's say that event A occurs, and it will schedule B and C. Remember, the thing to keep in mind with event graphs is the way they work is that the scheduling does not go anywhere. That's not a useful way to think of this. What the scheduling does is it simply puts the events that it schedules on the event list. So when event A occurs, it's going to schedule B and C, maybe with some delay. Okay, so at some point then, the event list, as it's processing things, eventually event B is going to occur. And when it occurs, then the listener is going to hear that. And then, in this case, because it heard an event that it has, it will schedule, it will just process things the way it has. If it has a state transition, it'll perform that state transition and then schedule whatever events it has. In this case, it'll schedule one event D. Now, at some point, the event C will be heard, will be scheduled, and that will be heard, but the listener will say, hey, I don't have a C, so I'm just going to stick my fingers in my ear and go, la, 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 I can't hear you.
This is essentially just like a signals and slots program, but with the event graph.
Yeah. So, I mean, here's an example. Like we have our arrival process, and in this case, like this diagram, now, What these boxes are representing are instances. And so if we have two arrival processes, those could be two completely separate instances of an arrival process. They would each have their own inter-arrival times, and then they would each have their own state variables that were counting the number of arrivals. But supposing, for whatever reason, we had these two arrival processes happening, and for whatever reason we wanted to count the total number of arrivals in each one. So here's a simple event graph that would do that. It has just one state variable. I'm calling it H for whatever reason. And every time it hears an arrival, it's going to increment it. Now, its run event is going to initialize that to 0. So at any given time, this state variable will give the total number of arrivals for both of these. So the way that it works is that this arrival process has an arrival event. When that occurs, that's heard by the arrival listener and it increments its state variable. Every time this arrival process has an arrival event, its arrival event is heard by the listener and it updates it. Okay, this is a somewhat artificial example, but there are situations where you have these different pieces and they've been designed to do one particular thing and you want to do just a little bit more. What I would point out is that what you're doing is we're adding functionality to the totality of the model by simply just adding a little bit of stuff. I mean, this is about as small an event graph as you can possibly get. But it adds functionality. In other words, it gives you a value that, in this case, summarizes. And no matter if we had many arrival processes, this would still capture the total of all of them, if that's something we're interested in. Okay, a more concrete or useful example is the simple server component. And the motivation here, the idea is that when motivation for this is noticing, among other things, that this pattern shows up again and again. We saw it, by itself in the arrival process. We saw it as part of the multiple server queue. We saw it even in the transfer line. We go back to the transfer line, we see that here's just this piece is just its own thing. So the idea now is that instead of having both the arrivals and the server piece, the simple server component is just a server part of the model. It leaves out the specific arrival sequence. It's agnostic to that. And all it cares about is that some other component just needs to produce some arrival events that it hears. We have one in the arrival process, but it could be any component that schedules arrival events can be used to produce customers for this server. And so the simple server component is it's kind of a stripped down version of the multiple server queue. So we don't because we're not modeling the arrivals, all we need are the service times and the number of servers. Okay, so we're going back to our multiple server queue situation. We have the same two state variables, only now I'm going to add the number of service completions, because that's something that we would potentially be interested in. Not the number in the system, the number of service completions. And the component now looks like this. Okay, now notice what's missing. What's missing are the self-scheduling arrival events. Okay, so it has a run event which initializes its 3 state variables. The arrival, start service, and end service are all exactly the same as in our multiple server queue, with the exception in this case of we have an additional state variable that is the total number of service completions, which would only be incremented when we have an end service event. So the end service event is what the event graph captures as a service completion. Now the thing about this component, as opposed to a model, is that if we were to implement this just as it is with nothing else, what would happen? I mean, how would this proceed?
It's not gonna do anything.
Yeah, it's going to do a little bit. It does have a run event. Remember, the run event is always on the event list. The run event is going to initialize its state variables and then do nothing. Why? Because nothing gets scheduled after the run event. So it's not going to do anything. But in other words, to create a model, we need to drive it with something. So to recreate our multiple server queue model, we need to drive it with an arrival process. So an arrival process by itself will produce a stream of arrival events, and each of those arrival events will be heard by our simple server component and then kick off the whole other thing. And so, if the contents of these boxes are understood, again, this is not, these boxes represent instances, not sort of templates. In other words, when we kind of just write the event graph, this is analogous to writing a class. The box is analogous to instantiating the class. So here we have an instance of the arrival process, an instance of the server, and the instance of the server is listening to the arrival process. And this is, to kind of see the full picture here, this is kind of what it looks like. So our arrival process is so we have a run event here and a run event here. So now we're going to be 2 run events on the event list, and they're both going to get processed. The order, now, because this is where kind of encapsulation becomes important. Each component should encapsulate its state variables, meaning that the only thing which can change the state variables is that component itself. And what that allows us to do are things like, well, here, the n that we had in the arrival process was counting the number of arrivals. The n in the server component was counting the number of service completions. And because these are entirely separate components, even though they happen to have the same letter name, those are 2 entirely different state variables. The order of run events is, or at least should be, arbitrary and irrelevant. In other words, it doesn't matter which order they are implemented in, because each run event is only going to initialize the state variables for that component, and because if they are encapsulated, then they shouldn't affect each other. And therefore, the order in which they're executed, the run event is executed, is arbitrary and shouldn't matter. But at some point, both of these run events will be executed by the event list. This run event will schedule the first arrival. And then when that arrival occurs, it will perform this state transition, incrementing n, and schedule the next arrival. And then that arrival event will be dispatched to its listener. In this case, The server component will hear arrival and say, oh, I've got an arrival. And so it will execute this arrival event as if it had scheduled it, perform its state transition, say if there's an available server, schedule, start service, and then everything is going to continue like that. Okay, and this is the model that I'm going to have you implement in the next computer assignment.